Okay, so we can start. So there is this last part left, which is proximal gradient descent. So this is useful for functions which are composite type. So meaning these are of the form fx plus gx, and we want to minimize this f. Where f is differentiable, small f, and g is proper LSC, okay, lower semi-continuous, and we assume that the problem is well defined, meaning minima exists, and that's it. So so for such type of problems where g can be non-smooth but f is smooth because it's differentiable, so for such a problem we can think of proximal gradient descent. So that's the topic today. So we define this algorithm so let x naught in RD gamma greater than 0 step size, then the proximal gradient descent algorithm is defined as xt plus 1 is prox lambda g xt minus gamma grad f xt. Okay, so this is a proximal gradient descent method. So and we recall the proximal operator g of x is argmin g prime of gx prime plus norm of x minus x prime, this argmin over x prime. Okay, we also put a half there. When we take a derivative, then it will get cancelled. So this is the proximal operator defined. So in place of g, you will take lambda g. So so this method is useful for functions like this. So here there is f plus g, but there you have f, and then this g is here in the proximal. Okay. So this type of algorithm is used to minimize functions like this. If you encounter problems like this, f is differentiable plus non-smooth, then this is the algorithm with a guarantee of convergence. Okay, so so then we will go directly for the convergence. So let us try to prove that this algorithm converges. So this is theorem 10.3, and consider composite functions, and g convex, f convex, L smooth for some L greater than 0. Let xt be the sequence of iterates generated by PGD with step size gamma in 0, 1 by L. Then for all x star in argmin, then for all x star in argmin of f, for all t, we have that f xt minus f x star is less than equal to x naught minus x star by 2 gamma t. So this is the convergence result that we are interested in. Okay, so this is specifically for composite. So these terms are fixed in some sense, right? So the minima will be some fixed number, fixed vector. Let's say this is initial vector, this is a constant. So as t grows, the iteration grows, the PGD method, this will go to 0, meaning that fxt becomes fx star. okay, meaning xt become x star. Okay, so this is the guarantee that we have. So let us try to prove this. Okay, so let x star be any minimizer okay, let us say that is any minimizer. Then we look into two quantities, let's say fxt minus fx star, and we also look at xt minus x star. Okay, we look into these two quantities as first steps, okay, before we get there. So the few things that we have is this is decreasing. Okay, so first we saw that this is decreasing. Okay, so let us say this is the first claim, that fxt minus fx star decreases. So we will prove this claim. So with this we can write the update xt. Basically we have to look into the PGD that we wrote, and the PGD was and then we will substitute the gamma g again. Okay, so we are supposed to use the PGD algorithm. So if we use the PGD algorithm, then basically it's with the proximal, and the proximal further has the definition in terms of argmin. Okay, so what we can do is we first write the proximal step with lambda with gamma g, and then we expand that. So by PGD, what we have is that xt plus 1s are generated by prox gamma g xt minus gamma grad f xt. So this is the iterative algorithm that we are trying, and then we use the definition of prox gamma g, right? So prox gamma g, the definition of the proximal of prox, let us say g of x. We just recall the actual definition. So argmin g x prime plus half norm x prime minus x, and this is x prime. So now we have to use that definition with, in place of g we have lambda g, gamma g. Okay, so this is equal to argmin of let us say x prime and g, lambda g x prime. I mean yeah, so what we have to see is in place of x we have this whole thing, right? Other places which is x prime remains the same, but the place where we have x we have to substitute the whole thing, right? So it's fine. So the first one is argmin of gx prime, so this gx prime plus half of, now in place, okay, x prime minus, it's written the same way. Sometimes in the norm they flip, but in this case also it's the same. Okay, so x prime minus, I was thinking should I write this first and minus x prime. It's okay, if we need it then we will change it, xt minus gamma f xt. Okay, so in place of x we put this guy here. So now this is x prime minus x, in place of x we have that. Okay, so then we will do well, I mean this is our template, and then we will see what happens if I replace x prime by xt plus 1. This implies gx t plus 1 plus 1 by 2 gamma x t plus 1 minus xt minus gamma grad f xt is less than equal to g xt plus 1 by 2 gamma xt minus xt minus gamma grad f xt. Okay, so this implies this, right? So what we have done is in place of x prime we substituted xt plus 1, and we also substituted in place of x prime xt. Then the term with xt plus 1 is lower. Okay, so why was that? Yeah, so at xt plus 1 is the minimum, right? So then this will be lower compared to xt. So now we will rearrange, and before rearranging what we will use is the fact that f is L smooth. So our goal is to go up to this, and what we have in hand is the the term with g, so we have a smoothness for f. Okay, so fxt plus 1 less than equal to something, and then that inequality, this inequality will be added up, and then we get the capital F, because capital F is small f plus g. So now we will make use of the fact that f is L smooth. So given f is L smooth, fxt plus 1 minus fxt, so this is just the definition of smoothness that we have seen a couple of times, xt plus 1 minus xt plus L by 2 xt plus 1 minus xt. Okay, this is the smoothness definition, and from here what we really want is f and g aligned with t plus 1 and f and g aligned with xt. Okay, and then we will add. Okay, our objective is to get to fxt minus fx star. So we can move this fxt on the right, or we move the gxt on the left, and remaining everything we put on the right side. Okay, so doing all this little bit of algebra, we can skip that, and we will say that we'll just add and rearrange. Okay, so if we just add, then we will have this guy added with this guy, and then minus, because g will come here, so that will be minus capital F xt, and remaining terms I believe I will keep it on the right. Okay, and some cancellations also happen. So let me write that, and then should be fine. Okay, so xt plus 1, and so this is like adding. Okay, adding the two, then we have minus f xt, and this is less than equal to so basically minus 1 by 2 gamma, right, and there is one gamma square, but right, so minus 1 by 2 gamma I can see xt, well that one gets cancelled for sure, and xt plus 1 minus xt norm square I see here. So I will write down this, and it's easy to convince that this is indeed the case. So xt plus 1, so what remains is this, plus L by 2 xt plus 1 minus xt norm squared. Okay, so we can kind of check that this is indeed correct, because the last term is anyway already matching with this. So the only thing we need to check is this guy. So this is the guy that remains. So xt plus 1 minus xt, basically I see this directly coming from here. Okay, so this is directly coming from here, minus 1 by 2 norm xt minus plus 1 minus xt square is there. So it seems that the other terms are getting cancelled. Okay, so it seems to be correct. Okay, because there you see xt plus 1 minus xt inner product with this, and there is also xt plus 1 minus xt inner product with this, and gamma got cancelled, but what happened to the 2, right? There is, I see additional 2 here, so this gamma gets cancelled, right? Inner product of xt plus 1 minus xt with grad f xt I see, gamma gets cancelled for sure, but 2 is here, right? Oh, but there is 2 coming with the inner product itself, right? So 2 will also get cancelled. Okay, so 2 times xt plus 1 minus xt, inner product of xt plus 1 minus xt minus this, and then 2 gets cancelled, gamma also gets cancelled. So basically we get exactly this here, so they get cancelled, inner product. So this is correct. Okay, and this term is 0. Okay, so this is equal to 0. So this means that this is decreasing, because it's for any conjugative t, we are saying that the t plus 1 and difference with it is less than equal to 0. So this means that fxt plus 1 is less than equal to fxt for all t, means that fxt is a decreasing. Okay, so this is less than equal to 0. Now our second claim is that we said, so we looked into this, and now our second claim is that this also is decreasing. Okay, so we will prove that this is also decreasing. Now we claim that norm of xt plus 1 minus x star is decreasing. So for this we look into the term 1 by 2 gamma xt plus 1 minus x star squared minus 1 by 2 gamma xt minus x star squared. So let us look into this term, and so the next step is obviously to expand this. So if we expand this, then I mean some simplifications will happen. So what I want to write is xt plus 1 minus xt, right? And then okay, so maybe I will write down and then we will figure this out. 1 by 2 gamma and then xt plus 1 minus xt and minus xt minus xt plus 1 by gamma and xt plus 1 minus x star. Okay, so this is the claim that this is equal to this. So this is norm of xt plus 1. So a plus b whole square form, let us say x star minus 2 xt plus 1 x star. Okay, and this is our first term, and then our second term is with minus. So this is norm of xt squared plus norm of x star squared minus 2 xt x star. Okay, so basically everything should follow from here. So xt plus 1 and then ic x star are getting cancelled. So 1 by 2 gamma x star squared and minus 1 by 2 gamma x star squared. So we can get rid of this. And then we have to do this simplifications a little bit. So what we have is 1 by 2 gamma x t plus 1 whole squared and minus 1 by 2 gamma xt whole squared. And then we have minus 2 x star is common. Something more is also done here. So let us do this. So what we have is 1 by 2 gamma xt plus 1 whole squared and minus 1 by gamma, and I'm going to like take this x star common from that inner product, so that also 2 gets cancelled. So it's also 1 by gamma. So 1 by gamma xt plus 1, and this minus because plus, right? So so if I retain the minus, then okay, so the way is right now is, yeah, it's fine. So but then I have a plus there. Okay, that's interesting. So 1 by gamma, but right, so let us take minus. Okay, so minus and then xt plus 1 minus xt I'm getting, right? So but here, so let us see. So xt plus 1 minus xt and then comma x star. So we have taken this, and then what we have is minus 1 by 2 gamma xt norm of xt squared, right? So let us check this again. So especially the inner product term. So the norm terms are okay. I mean there will be minus, yeah, that's fine. So x minus 1 by gamma and minus becomes plus there, right? Yeah, that's fine. Overall it should be plus. So then it's xt inner product with x star. So this gamma obviously can go inside. You see there is this xt plus 1 term extra there. So some add and subtract might have happened. Okay. So for the moment what I can do is this gamma I can take inside, try to make as close to possible. But then you see there is this xt plus 1 on the second argument of the inner product. There is add and subtract. So if we do that with 1 by 2 gamma, so I'm thinking about the inner product, like I mean how the inner product gets changed, right? Because in the inner product I have x star, and from here I will get xt plus 1 inner product, and the second term will give me, the last term will give me the other one. Okay, I see. So okay, so let us, as a first step, let us just write down this as one line, and then we will, so this is xt plus 1, and then we have, so what I will do is that I will expand this immediately, because so this is xt plus 1 okay, that's the inner product, and then this is the second one, which is xt plus 1 minus xt by gamma, and then x star, and then minus 1 by 2 gamma, and we will expand this as well. So xt. Yeah, it is pretty possible, I guess. If you expand this, it should be this. So you want to complete the square for the first term, xt plus 1 minus xt, right? Yeah. Okay, let us do that. So the first thing is to look at the inner product. So inner product will be xt plus 1 xt. Where do you give this? Xt plus 1, where do you have xt plus 1 xt as inner product here? Yeah, I mean I completely agree. I still, yeah. Yes, you are right. Yeah, I'm just figuring out like, can we achieve that by doing this add and subtract business? So is it sure? So what did you say? Add and subtract next? Oh yeah. Okay. So we we subtracted but didn't add. Okay, that's a bit silly. Okay. So this is xt plus 1, xt plus 1, right? Okay. Now let's write this on the board and see if we have a good one. Okay. So let us say add and subtract xt plus 1. Okay. So 1 by gamma xt plus 1. So this is the add one, and let us say also subtract 1 by gamma xt plus 1. Okay, let us see if this helps in any way. Second, fourth, and fifth term. Okay, let us see. It becomes first term of the RHS, this one. It makes a square. Okay, let us see. At least we get one term. Second, fourth, and fifth will be this one. Okay, so let's see if this completes a square for yeah, xt plus 1, xt inner product I see, and 2, there is a negative there, but that negative gets cancelled, and so this is indeed 1, so 2 there gets cancelled as well. So minus 1 by gamma inner product, that's fine. So inner product is settled and norms are also settled. The only thing is that this is in the negative of that, so which is what we want. Okay, so let us say this is 1, 2, and 3. So 1 plus 2 plus 3 is equal to minus 1 by 2 gamma norm of xt plus 1 minus xt squared. Okay, so this is kind of settled. Then let us focus on the remaining terms. And remaining terms, xt plus 1 minus xt from here I see, and okay, okay, xt plus 1 xt is there, and then the second argument can be changed. Okay, now I see. So exactly, so first and the sixth term, it will be my focus, and then using this we will have this argument common, then this will appear. Okay, this is the plan. So yeah, exactly, so that will also combine. So we wrote this as a first term, right? So let us make this 0 then. The 0, 1. Oh, the way we wrote is not the term name of these terms are 1, 0, 1. So this is our 2, and this is our 3, and this is our 4, and this is 5, and this is 6. Okay, so this was 1, 3, and 6, right? 1, 3, 4, sorry. 1, 3, and 4 gave us this. Now we focus on, okay, so let us make this 0, 5, and 6. This is the second iteration, so 2 circles. So 0, 5, 6 is, if you see 0 and 5, then they are the same. So half plus half becomes 1. So that's 1 by gamma norm xt plus 1 squared. But we will not make it a norm, we will keep it inner product because we will combine it with this. So 0 plus 5, this gives us, so let us do this one more step for this. So this is 1 by gamma xt plus 1 xt plus 1, and minus the sixth term is 1 by gamma xt plus 1. Okay, so the second argument is common, so now we can subtract. So this is 1 by gamma xt plus 1 minus xt. So now since we got the first argument common, now the second argument can combine as a third step. So this is 1 by gamma xt plus 1 minus xt and comma xt plus 1. Now we combine it with the remaining term. So remaining term is 2. Okay, so the 2 is the third step. So if we add the 2, then fact that the first term is common, we have that xt plus 1 minus x star. Okay, and the negative should be okay. Yeah, because the first argument for us is a little bit flipped one. So if we have to match exactly that, then we can absorb the minus xt minus xt plus 1 we will do, and here also it will give us 1 minus here, and then it will be exactly in the form there. Okay, so this more or less is clear, so we will not spend time on this. So this and this gets added to give us the second term, which is this one. We already got this one. Okay, so this proves this. Okay, then now we use the fact that xt plus 1 comes from the PGD, which is the proximal gradient descent. So we will use that fact to conclude on where is this, right? So where is this iteration going? I mean, this is a, we want to see this as a subdifferential. So that will be our next claim, that this belongs to subdifferential of grad f plus subdifferential of g. Okay, that is our claim. Since xt plus 1 is coming from the proximal, xt minus xt plus 1 will belong to grad f plus subdifferential of g. Okay, that's the next step we are trying to. So since xt plus 1 is proximal of gamma g and xt minus gamma grad f xt, so there was a result that we recall. So this result said that G RD to R and proper LSC, which is all given here, convex, then P is equal to proximal of proximal G of X if and only if X minus P is in the subdifferential of G P. Okay, so this is the result that we are going to use here. Okay, in our place P is xt plus 1, right? So xt plus 1 is proximal of X. In our place X is xt minus gamma grad f xt. So then this implies that X minus P, right? So in our case this will be this guy minus this guy will be in the subdifferential of gamma g. Okay, so using this we can write that. So this implies that, so as I said, P is our xt plus 1, X is our this. So this result says that X minus P, so which is xt minus gamma grad f xt minus xt plus 1 is in the subdifferential of lambda g in our case. Okay, in our case it's lambda g and not g of xt plus 1. P is xt plus 1. So we can solve for this. So overall, if we solve for this, then xt minus xt plus 1, this implies xt minus xt plus 1, and then we also divide by the, and it was gamma, yeah, it was gamma, right, not lambda. So it was gamma. This is gamma. Okay, so what we will do is that xt plus 1 minus xt will belong to, we move this on the right hand side. Okay, so we did a little bit of subdifferential calculus in the beginning. We are allowed to do that. We are allowed to, because this will be a set and this is a fixed number because f is differentiable, so it's a unique number. So we are allowed to add this number to the set. Okay, so this inclusion still remains. Okay, we did this before. So fxt plus set addition gamma g xt plus 1, and then we are also allowed to divide by gamma. Okay, so all this is valid with subdifferential calculus. So xt minus xt plus 1 by gamma is in grad f xt plus gamma g xt plus 1. Okay, yeah, these are advanced stuffs, right? This is real advanced calculus. No one will teach you these things in introductory optimizations. Okay, this is taught to postgraduate students, usually master's or doctoral program. Okay, so right, so the next step is, yeah, so our plan was to look for the eta in the inner product that we had. So anyway, so let us see, because if you remember the first item of the inner product that we were working on was this guy. So this guy is now known to be a subdifferential of basically in the derivative of this fxt and this, right? So I will write down the first the one that we derived. I think it's good to write down so that you have a context of what we are doing. So we already did this, xt plus 1 minus x star square minus 1 by 2 gamma xt minus x star whole square, and this is minus 1 by 2 gamma xt plus 1 minus xt minus xt minus xt plus 1 by gamma xt plus 1 minus x star. So this is something we derived, and just to put in context, I wrote it again, and we are focusing here. And what we are saying here is that this is this is in the derivative of this f computed at xt and the subdifferential g computed at t plus 1. Okay, so if this quantity lies there, then there must exist a gradient, because there could be multiple gradient, because this is subdifferential. So we remove this also because we divided previously. So there must exist some eta here in the subdifferential, so that eta plus this will be this, because this is a unique, guys. So there will be, this is unique. So this plus some vector eta will make sure it will be equal to this, because this guy belongs there. So there must be some eta for which we can produce this. So then so from star there exists some eta t plus 1 in subdifferential of g computed at xt plus 1, and for which so basically we will replace that first argument in the inner product by this eta t plus 1. Okay, so then so basically, without rewriting things again, so we will continue from here, and this is equal to minus 1 by 2 gamma and norm of xt plus 1 minus xt square grad f xt plus eta t plus 1 xt plus 1 minus x star. Okay, so we use this fact that xt minus xt plus 1 by gamma is grad f xt plus some eta t plus 1 from subdifferential of g. Okay, so then I believe there is a splitting. Yeah, eta. Yeah, there is a splitting of this inner product, and then t plus 1 minus xt grad f xt. Okay, there is some add and subtract here, it seems. It seems that grad f xt and xt are added and subtracted. So grad f xt xt minus grad f xt xt. Okay, these are added and subtracted. So if we do that, then we have so we can do it here. Okay, so with this we have minus 1 by 2 gamma and xt plus 1 minus xt eta t plus 1 xt plus 1 minus x star minus grad f xt xt plus 1 minus xt plus grad f xt x star minus xt. Okay, so I believe this is okay. So the first term seems fine. Second term is grad f xt. I mean, eta t plus 1 goes with xt plus 1 x star. That's also clear. Grad f xt goes with xt plus 1. Grad f xt goes with xt plus 1 minus xt. It's there. Grad f xt goes with. I'm just looking at the minus or plus sign. That's it. But it seems to be okay. And then grad f xt also goes with x star minus xt, which is also okay. Okay, because grad f xt goes with x star and grad f xt goes with xt. So grad f xt goes with x star minus xt. On the first inner product term, we can use that eta t plus 1 goes in subdifferential of eta t plus 1. We know that it goes in the subdifferential of g at t plus 1, and hence we can use the condition that a vector is a subdifferential, right? So there is this condition that we will exploit and it will give us some inequality. So we use this definition of the subgradient. So the fact that eta t plus 1 is in the subdifferential of g at xt plus 1, then using the definition of subgradient, okay. So the definition of the subgradient told us that this is like fx minus fy minus eta y minus x, right, is greater than or equal to 0. Then eta is the subdifferential. Okay, so that's the inequality we are talking. That's exactly the definition of a subgradient, right? G is a subgradient of f if fx minus or fy minus fx plus inner product of eta with y minus x is greater than or equal to 0, right? So basically for in this context, this exactly means that eta t plus 1 xt plus 1 minus x star is which is eta t plus 1 x star minus, we observe the minus t plus 1 is less than or equal to g x star minus g xt plus 1. Okay, so that's the inequality I was talking about. This gives us this inequality. The very fact that eta t plus 1 is a subgradient, this gives us this inequality. Now on the second inner product, we can use the smoothness of L. So the second inner product, we will use the smoothness of f, basically the L smoothness. So in the L smoothness term, we have this inner product there. So that will give us for second inner product. So for second inner product, we have that minus grad f xt xt plus 1 minus xt is less than or equal to L by 2 xt plus 1 minus xt squared plus fxt minus fxt plus 1. So this is the L smoothness of f. We have just written the definition of that, and this will follow from there. So we are interested in the upper bound, right? But already like negative is there, so that's fine. So we have written this L smoothness, and we have this negative term also. So this negative term we will upper bound. So that's fine. Usually when we do convergence analysis, we usually focus on these inner product terms and bound them with the function values. Okay, so here we are doing exactly that. We tackle the first inner product and some function value, second inner product some function value, and also difference of x. So then on the last term, which is again an inner product, we will use convexity of f. Okay, so when we use convexity of f, again we will have some function values bounds from there as well. So then we have all these inner products bounded by some function values. For the third inner product, so for the third inner product, we basically use the convexity of f, then we have grad f xt x star minus xt is less than or equal to fx star minus fxt. Okay, that's the definition of a convexity. So this is the first order definition of convexity. So now we use all this, these three inner product bounds that we have. So let us say this is A, this is B, and this is C. So using this, combining A, B, C, we get so we can copy over the left hand side that we had. These are all the right hand side going on. So we can copy over this. So xt plus 1 minus x star minus 1 by 2 gamma xt minus x star whole squared, and these guys were bounded by these, right? So and these are further bounded by these arguments. So overall we can write this as less than equal to, let's just check this small things first. Okay, xt plus 1 t is there, and there is L by 2 term there, and then remaining. Okay, that's fine. So all this is less than equal to, yeah, it can fit here maybe. So less than equal to minus 1 by 2 gamma xt plus 1 minus xt square L by 2 xt plus 1 minus xt squared plus g x star minus g t plus 1 plus fxt minus fxt plus 1 plus fx star minus fxt. Okay, so basically we have used all this a, b, c. Okay, so there shouldn't be an issue there. So now since we have this f and g, we remember that our goal is to work with capital F. So wherever f and g have the same argument, we will add them to make capital F. So this is capital F of x star, and then this is minus capital F of xt plus 1, and then with t also maybe. T, it gets cancelled, right? Okay, so t gets cancelled actually. So this is what we have. So we will write this simplified form. So this is equal to minus 1 by 2 gamma xt plus 1 minus xt plus L by 2 xt plus 1 minus xt, and then minus of f xt plus 1 minus fx star. Okay, so we have added those f to get capital F, and overall these guys are less than equal to. Okay, that is interesting because okay, so what is written next we have to see. So this should be less than equal to minus of f xt plus 1 minus fx star. Okay, so we already have that term, and what we are saying is that this is necessarily greater. This is necessarily greater, right? So basically what we are saying is that this is already greater, but what we are saying is L by 2 minus 1 by 2 gamma is negative, right? So here note that this is because L 1 by 2 and L minus 1 by gamma, and previously we wrote in the theorem that gamma lies in the theorem gamma lies in 0 open 0 1 by L. So this means that gamma L is less than equal to 1. Okay, or yeah, so gamma L is less than equal to 1, or L is less than equal to 1 by gamma. Okay, so then this guy is negative. So this is less than equal to 0. So if we drop a less than equal to 0 term, we retain the upper bound. Okay, so this is the so what happens after this, right? So we have, so now that we have established that the iteration gap, which is this, we are calling it this as iteration gap, and function values are decreasing. So we want to show that the combined okay, so we have shown that iterate gap and function values are decreasing. Earlier we have shown that this is decreasing. We have proved that as a first part of the theorem. So basically what it means is this is getting closer and closer to fx star. Okay, so I mean that's what we have seen. So as t is increasing, this is decreasing, so meaning it's becoming more and more negative. So what does this say about the left hand side? It's becoming more and more negative. Basically it's decreasing, meaning the left hand side is also decreasing. Okay, that's what it means. So left hand side is decreasing, meaning yeah, this guy is getting, what does this mean, right? The difference between this is getting, I mean they are getting closer. Okay, so that's how we read this. So the xt plus 1 minus xt compared to xt minus x star is becoming more and more kind of decreasing basically. And this guy is always greater than equal to this, because this is the minimum, is a minimization problem. So this guy is always going to be larger than equal to this. So this will be some positive quantity, but this positive quantity is decreasing. right? So I hope we have a good understanding of what is going on, right? So the difference between ft plus 1 fxt is getting so what I'm trying to say is like what is happening to this and this. We are getting xt plus 1 minus x star is getting closer to xt minus x star, because this is anyways upper bound. So what it's saying is that because the way I see this is that this is always larger than this, so it will be larger, but then as t is increasing it's getting closer to this. So basically this is becoming 0 from the negative. So let us say it eventually becomes 0, then initially for some t it's here, then t plus 1, this difference is getting closer and closer to 0, but it will remain less than equal to 0 for sure. So it doesn't give us anything concrete, right? Yeah, it's one thing it says for sure is that because this overall it remains negative, okay, like maybe I should not look into this difference, but what I know for sure that this will be less than equal to 0. I mean this is positive, so hence overall this is negative. So what we say is that this guy is this is less than equal to 0, meaning this is less than equal to this. Okay, so let us at least put this in the note so that we have, that is what we can conclude is that 1 by 2 gamma, or 1 by 2 gamma gets cancelled. So what we really are trying to say from here is that xt plus 1 minus x star is less than equal to xt minus x star. So that is something we can conclude for sure, because overall this guy is positive, and with the negative this negative. Okay, so let's see. So then we will introduce. Let's see. So overall, what we have said is the two quantities we are looking at: capital F x t plus 1 minus f x star. We have done, or in fact x t. Then that was also decreasing in the first proof, and this guy is also decreasing. Then combined with this, we will build a Lyapunov energy kind of construct and see what happens to that. So so we will construct. So when overall we will show that the following Lyapunov energy, which is defined as 1 by 2 gamma xt minus x star plus t f xt minus fx star. Overall, we will show that this is decreasing. So to show that this is decreasing, we will show that et plus 1 minus et is less than 0. So to do that, we will take the difference et plus 1 minus et, which is after simplification it becomes fxt plus 1 minus fx star and minus t fxt minus fx star plus 1 by 2 gamma and norm of xt plus 1 minus x star plus minus 1 by 2 gamma and norm of xt minus x star whole squared. So this is the et plus 1 minus et looks like, and then we will do some simplifications which are perhaps evident. Yeah, these are evident. So next step is equal to fx t plus 1 minus fx star plus t basically, and then fx t plus 1 minus fxt plus 1 by 2 gamma norm of xt plus 1 minus x star whole square minus 1 by 2 gamma xt minus x star whole square. So what did we do here? We xt plus 1, so maybe I'm missing something. Is correct, right? Yeah, the one I mean went with fxt plus 1 and then minus fx star also, and then the remaining t multiplies that. So and then the third term was minus t. Okay. So this is using the difference of fxt plus 1 minus fxt term. We are going to use that. So this is like less than equal to, and I can put this as ABC. So let us say this is D. This is fx t plus 1 minus fx star plus 1 by 2 gamma xt plus 1 minus x star minus 1 by 2 gamma and xt minus x star. And this is from the D, which was fxt plus 1 minus fxt bound that we had before. So that was used, okay. So this bound that we had was used, meaning, just for the sake of notes, I write this so that so I just write this quickly. Fxt is less than or equal to minus 1 by 2 gamma and xt plus 1 minus xt L by 2 and xt plus 1 minus xt squared. I mean, the idea was that this is less than or equal to 0. That was the more important part. So, so that's how we got rid of that. We bounded it by 0, so that got away. The t term got away, and everything else is as it is. So, and eventually we will also use this this bound that we had also for these guys. I mean, this guy. This is the recall part, so I put this in bracket in a box, and then so then we further, as a next step, we are saying that we have found a bound for this as well in the previous steps, and this was less than or equal to 0. So it was less than or equal to negative of f something, right? We did that. So this is less than or equal to 0, right? So this whole thing is less than or equal to 0. We have so overall it's less than or equal to 0. That's what we are trying to claim, right? So this is overall it's less than or equal to 0. So we have shown that the Lyapunov energy Et is decreasing with t. Okay, so this implies that Et is decreasing with t. So this means that we can write Et is less than E0, but Et will be greater than or equal to this t, right? That's fine. So we can write that as t f xt minus fx star, which is less than or equal to Et, because Et has the norm plus norm term as well. So if I drop that, then it's lesser than Et, and then this is less than or equal to E0, because Et is a decreasing function, so it must be less than the initial value, and initial value was 1 by 2 gamma and x naught minus x star whole squared. And the conclusion follows by dividing by t both sides, right? So we have that fxt minus fx star is less than or equal to norm x naught minus x star by 2 gamma t. The idea is to do a lot of practice so that if needed, then we know what are the steps. So